Okay, hello everyone. Thanks for having me. So gonna break this up into a few sections. So any engineers in the audience, I'm gonna have to beg you to could somebody put the slideshow? Thank you. Bear with me for 5 minutes. If you find this, find the first 5 minutes a bit simple. But what I'm going to do is I'm going to first explain what a metal is, and that might sound a bit simple, but and how they actually work and why they are fundamentally strong. And then I'll move on to what happens when you put them inside a nuclear reactor and all the problems that we get from that, and all the challenges we have in keeping our nuclear reactors operating nicely and safely, and helping keep the lights on, essentially. And then I'll move on to a little bit about fusion, because everyone likes fusion. It's the new thing. Well, it's been the new thing for 50 years, but it's still the new thing. But yeah, so in terms of, so we're gonna think about things on the scale of atoms in this talk. So if you think about so on the scale of atoms, there's 2 types of materials, and I've been told that Sarah studied plastics, which are a bit of a halfway house, but never mind. But there are two types of materials. There are those that are crystals, and there are those that aren't crystals. So all a crystal is the atoms are arranged in a nice, neat arrangement. It's like tiled floor, or there's no randomness. Everything is just nice and neat in a row, beautiful, aligned. You can stack them different ways, but they are stacked in a nice, neat arrangement. So something that isn't crystalline, we call a glass. So literally, your pint glass is not crystalline. And metals very much fall into the category of crystals. Most people tend not to think about this. If you ever come across the people who believe in crystal magic, I say, why don't you sleep with a lump of metal under your bed? It's that's got more crystals than anything else yours have. And there's a little example of this. We can actually see this. So most people, when they're out on a walk, stop and smell the roses. I stop and look at lampposts. Next time you're out on a walk, have a look at a lamppost, and you'll see these little patterns, these darker areas and these lighter areas. And these are literally crystals, metal crystals, you can see. Most metals, the crystals are so small that we can't see them by eye. There are a few examples like this where they are actually big enough to see them by eye. So that's what a metal is fundamentally, or at least that's what it would be if everything was perfect. Nothing's ever perfect. So within that, we have a lot of defects, essentially. And there's one main type of defect that I want to talk to you about. It's very important. So if you imagine you hit something with a hammer and you leave a dent in it, you've actually moved material away. There was material there, and now you've left a dent, it's moved away. And we need to think about how that material actually moved. What's the mechanism that actually moved that material? Because if we understand that, then we can stop that from happening and strengthen our material. So the way this happens is there's a will it work? Well, it was working before. Or do I need to point it at your laptop? Please. Am I going to have to turn to Chris Whitty and say next slide, please?
What you need is a scientist.
Yeah. So, essentially, when the material moves, the atoms move across like a wave, essentially. And the way you can think about this is, are we good? Yeah. Imagine this book is, each page is a series of atoms. If I take one more set of another plane of atoms, and I jam it in there, I create what's called a line defect. So you can see the page that runs through, and basically it forms the shape of a line, and these lines move, and as we apply stress to our material, these lines move across, and this is actually the mechanism that's responsible for transporting transporting our material across and forming that dent when we've hit it, essentially. And we can see this. So if we put, we can see these in motion. Next slide, please. So these lines here are we can see them moving inside an electron microscope. So if you, that's a video. If you could hit play, please. I'm sorry, this is going to, oh no, go back. Hit play, please. Yeah. Play, maybe? No? Yeah, there you go, let's play that, let's play. Yeah, and we can literally see these, and this is, so this is what happens on, you know, on the scale of atoms when we hit something with a hammer, basically. These lines move through our material like waves, and they move our material across. Next slide, please. So essentially, if we can stop these lines moving in our material, we can stop that dent forming, we can make it stronger, we can make it harder. And how do we do that? We put obstacles in the way of it in the form of other defects in the crystal, and we've got a range of options. So for instance, this, right, why should I do this? How close do I have to get? There we go, right. So we can take an atom out, and we can leave a hole in it, or we can ram another atom, in there, or we can stick some different atoms in, or we can stick a load of different atoms in. Come on, yeah, and form a lump. And all these are basically different faults within our perfect arrangement of atoms that basically they're little roadblocks for our lines that move through. And these actually prevent our dislocation from moving. So this is quite easy to do. We can just throw some stuff. So we can just melt our metal, throw some stuff in there, and we do what's called thermomechanical processing, thermo heat mechanical hammer. So we just add heat and hammer, and combination of that, we can really actually tailor the metal to be what we want it to be. So I've done a lot of work on steel, so that's why I like to talk about iron and carbon. If you add carbon to iron, you get steel. So we've got a range of different obstacles that we can throw in there that will then stop these. And it's dead easy to do. We can do this. And if we do this, it's really well, you end up with essentially pottery. So every time, so if you've dropped a plate, right, next slide, please.
It's just shout.
Yeah, next slide. Yeah, just keep going. Next slide. There we go. And if you've ever dropped a plate on the floor, it smashes. So the problem is that if we do this too well, we get a different issue. And this is just a nice example. This is a nice example of actually these line defects. If we put enough of them in there, they can actually tangle in and of themselves, and it's literally, you know, like a ball of string tangled in itself, and they actually will stop each other from moving. So it's really easy to stop these things from moving. Next slide, please. All right, this is the only equation I have, promise. But the problem we have is if we have a crack in there and no material is perfect, there will be a crack in it. The people who look at these, you know, this graphene and these carbon nanotubes, and they've got these amazing strengths and everything. One of the reasons why that is because they're so tiny that statistically speaking, they're highly unlikely to have any defects. They are that small because there's only a handful of atoms in it, that they are probably perfect. But any sort of real macro scale material, it's going to have a crack in it, like it absolutely will somewhere. And essentially, if you think of that as that crack gets finer and finer and finer, the area of that crack is tiny. So if you've got a tiny area, any force in that area is going to cause a massive stress, and it's the stress that leads to our material fundamentally breaking. So we actually want our lines to be able to move a little bit, because if they do move a little bit, next across please, they actually absorb that energy at the crack and they blunt the crack tip, so then it doesn't move. So yeah, there's a crack in there, but we don't have to worry about it. So there's a sweet spot for our material where we want our lines to, we want these line defects in it to be hard to move, but not impossible to move. And so we spend a lot of time and energy making our material as optimal. It does exactly what we want. It's the exact strength. It's beautiful. And then we throw it in a nuclear reactor, and then we have to start worrying about radiation that mucks it all up for us, basically. I'll give you an example of what happens when you get this wrong. These are the Liberty ships. World War II. America joins the war. They need to make a lot of ships fast. So they switch from riveting their ships together, basically bolting out the place together, and they switch to welding their ships together. Welding tends to be weak. Added to that, they made these in nice room temperature dockyards, and then put them in cold Atlantic waters. Colder temperatures makes our dislocations harder to move, makes it more brittle, and that was a result. So we have to be very careful that we get this right. Next slide, please.
Alex, just try it yourself.
Oh, right. Oh, hey! There we go. Right. So, nuclear reactor is actually dead simple. It's a giant kettle. All we do is we get some uranium, stick it in the middle, do the fission, split the uranium apart, releases heat, boils the water, take that hot water off, go and spin a turbine and make ourselves some electricity. More specifically, it's a pressure cooker. So what we have is this giant steel drum around it that keeps the uranium in, keeps the water in, keeps everything in it, and we want it to stay in one piece. Right. Problem we have is when the uranium splits, releases neutrons, and these neutrons are the radiation that we really have to worry about. So we've got a little animation of what happens when a neutron comes into our material. So each blue dot here is an atom. Again, it's nice. It's a crystal, so they're in a nice, neat pattern. A neutron is going to come in over this side and smash everything up, basically, and it is literally playing pool with atoms. No, come on, smash. You might need to hit play, please. No. Yeah, there you go. Play. Miles, you play it a couple of times. Yeah, no, go on. Maybe. Maybe. No. Go on. Come on, neutron, I want you. Where are you? There we go. Oh, right, that was very rapid. Yeah, please. Yeah, I mean, to be fair, this happens on the time scale of picoseconds. So that's 10 to the minus 12. So it should be rapid, right? We'll go with that. But you can see, basically, the neutron comes in, hits this atom, that atom hits that atom, hits that atom, hits that atom, hits that atom. And we call this a cascade because it literally blows up. And what this effectively does is, in this tiny region, we effectively melt the material. And our atoms that were now nice and neatly sat where we wanted them to be have now all moved around. Now, metals have one good thing going for them and one great defense against it. They're simple. If I have a lump of steel, it's mostly iron. If I have one iron atom here and I knock it over there and it goes and it reforms the crystal, no harm, no foul. There was an iron atom there before, there's an iron atom there now, not a problem. So most of this actually recovers because this is where the pool analogy falls down. You knock your pool balls, they stay where they are. Because we have energy and the atoms are jiggling around, they mostly find their way back home. So this is basically how it tolerates the damage. Unfortunately, it doesn't do a perfect job. And now what we do is we're left with tiny holes in our material where an atom was and it's gone somewhere else and it hasn't found its way back home. And then we've got other atoms that are now wedged in between atoms where they shouldn't be. And these start to form obstacles to our dislocations, which we had tailored to just be the right level of immobile, hard to move, but not too hard. We're now making it harder for these things to move. And that's where that's where the problem starts. Next problem is that, again, atoms, we're above absolute zero, they have thermal energy, they're jiggling, they can move. And they can move into certain spots. So if we actually get holes, the holes can actually move and they can find each other, and they actually tend to like to agglomerate, they clump together. And what this looks like on a macro scale is this. This is a lump of steel that went into our before it went into the reactor. This is it as it came out of the reactor. It literally swells up on a tiny scale. So this is about a micron. So that's half a micron. So a micron is about the size of a single cell. These white dots that we can see are holes. We have literally turned the material into Swiss cheese. You imagine a piece of a notepad, a paper notepad with serrated edges. You tear a piece of paper off, very easy, because it's got the serrated edges. This is the exact same thing. Also, we tend to design things so that they fit together nice and neatly. That's now broken out of whatever position it was in, because now it doesn't fit. Next thing they can do, because they can do a lot of things. Take my analogy back of a line. What happens when we take a line and we tie it back on itself, make a loop? These things that as these defects that we've now introduced as a result of radiation. So if they can clump together in different ways. So now if I take a handful of atoms, I stick them in, there's nothing there, or it's a bit of a small bug. It looks all right from the inside, but now it's bulging out of the sides because I've just rammed a few extra atoms in there where they shouldn't be. And we see this as loops. And these things are tiny. These things can be tiny. They can be anywhere from 10 to 1,000 atoms across. But what happens, as I say, they bulged outwards. What happens if we stack millions of these things on top of each other and they're all bulging outwards in the same direction? That happens. These are zirconium rods that hold the uranium in. So, as I'm sure you realize by now, at some point our materials aren't going to work anymore. So the simplest solution is we take them out, we put a fresh one in. And a lot of the research is basically designed around when do we need to take it out and put a fresh one in. These are, so inside these rods is the uranium. We need to occasionally pull these rods out, stick fresh ones in, stick fresh uranium in. Those clumps of atoms are now all stacked on top of each other, and they've actually caused the rods to expand, and they're buckled, and now we can't get them out. So those rods were left in too long. A lot of research is around making sure that doesn't happen. What else can happen? Well, remember I said that if you take iron and you add some carbon to it, you get steel. Well, we tend to add more than just a bit of carbon. We add all sorts of other elements. So, and these can act as little obstacles, increase the strength. So we like to add a bit of nickel to our steel. We can actually, inside our microscopes, we can actually look at where these elements are. So for any physicists in the room, if you have an electron microscope, you've got a high energy electron coming in, that then excites the electrons around your atom. They jump off an energy level, jump back down an energy level, emit an X-ray. That X-ray has a very specific energy that correlates to that atom, to that element. So we can fire our electrons in, get some X-rays out, analyze those X-rays, and go, oh, we've got so many atoms of this type here, so many atoms of this type there. And we can literally map what happens to these elements, and they move. And they move in all sorts of complicated ways. Sometimes they like to clump together and form new, even more obstacles. Or sometimes we design, we actually wanted them to clump together in the first place, and then the radiation dissolves them. You can't win. You can see this was supposed to be round. This would have been round basically when it went in, and now it's all dissolved out. A lot of the research that we have is also around, back to the steel, back to the pressure vessel, is the pressure vessel is the one component that cannot fail. We cannot take it out. We cannot make a new one. If your pressure vessel goes, that's the end of your reactor. Yes, it's not financially viable to make a new pressure vessel. Build a new one. So a lot of research that we have is around what we call the belt line of the reactor. So this is literally the middle of the reactor, and is simple geometry that is closer to the radiation. So if you were, sorry, go on.
This one has a quick question.
Yeah.
How long do these pressure vessels last for? How long are they designed for?
So typically they're good for 40 years, and then after 40 years you will have a detailed monitoring program where you will monitor the properties over that lifetime. And if you get to 40 years and you go, actually it's not too bad, you can then apply to the regulator and say, can we have a few more years, please? And you can you can rinse and repeat that. So some reactors are going up to 60 years, maybe even a bit longer, depending on basically how well they've stood up to all this damage. So we look literally, so these are literally close. So we look at the center basically because it is physically closer to the radiation. If you were near a source of radiation, what would you do? You'd take a step back, because that would reduce inverse square law. The further up you are away, the weaker the radiation is. So the middle is the closest. And remember when I said that welds are a weak point? There is not a steels factory in the world that can forge a single forging of this. They are too big. That's a human, that's a piece being forged there, and that's a human for scale. So we design it so that the welds are not near the center, and we get those welds as far away as possible. But then we have even more problems. So this is a map of a pressure of this steel pressure vessel that somebody made, and then they chopped it in half. So the reason it's not a ring is because to make it into a ring, you will drill a hole in the middle, and then you will wind it round and round until it spreads out. But before you do that, it's a solid block. And what they did is they chopped it in half, and they looked at the where all the elements in there were, and you can see it's not uniform. And this is another big problem for us. So basically, when we're making our metals in the first place, as we put the small amounts of different elements in them, they're going to we melt it all up, and then each element has a different solidification temperature, and they solidify at slightly different temperatures. And what happens is some elements want to solidify, others don't, and the ones that don't get thrown outside of where the solid is, and we can see that it's not uniform. That's another problem we have to be aware of. That's going to change the properties, because we need to know properties of our material very well so that we can be sure that it's going to do the job that we want it to. So that's the most of the problem. That's sort of a brief overview of the problem with fission. Move on to fusion. What's the problem with fusion? It's the exact same thing. We've got neutrons, except that now we're turning it up to 11 because we've got a lot more of them. And this is essentially the major difference is we've got on the order of 100 times more neutrons coming out of it every second, basically. Yes?
Question online.
Yeah.
Alex. Is the reactor eventually forced to close because of metal embrittlement or erosion of the graphite in the core?
Can be it can be either. So yeah, it can be forced to close because of metal embrittlement. There was an issue with some Belgian reactors about 10 years ago. They did some scans of them and they found too many cracks in them basically than there should have been. So those had to get shut down whilst they did a thorough inspection. There's been all sorts of issues with them. There can be issues with the graphite. That's not my speciality, which is why I'm not talking about it, and I've only got an hour. But yes, it can be. There can be multiple reasons. This is only one. So remember going back to that picture of the lamppost, and we've got different crystals. There's a boundary between those crystals, and this is another type of defect that we have, and that's fine usually most of the time. Problem is that this boundary can actually attract other types of, so it's a defect attracting other types of defect. And when you start to turn this up to 11, you get transmutation. So not only do your neutrons come in, hit it, pings off, sometimes your neutron comes in and it absorbs it. And then what you have is an unstable isotope. And then it becomes radioactive. When that happens, this happens in fission reactors, by the way, as well, but when it happens to that degree, you can get different modes of decay. One of those is alpha decay. So what we're doing is, in order to get back to a stable isotope, it's going to emit 2 protons and 2 neutrons, which is a helium nucleus. It's inside a metal. Metals have a lot of free electrons. That's partly why they're typically conductive. So essentially you've just emitted a helium nucleus and it can pick up 2 electrons like that, not a problem. You've now got a helium atom. You've now injected gas into your material. And now you've got these regions where the gas likes to migrate to. This is one such boundary. This white line is helium inside your material. And we go back to that serrated paper. So before I go on, the next problem that we have is how to study this. So we can, so long as we can understand this, we can say, right, okay, it can take this much radiation, take it out, put a new one in for most of our components in a fusion design. Problem is that we need to irradiate it. We need to bombard it with that many neutrons to see what happens. We can't. There's only one place that you can get neutrons from, a reactor. So in the old days, when fission reactors were getting designed in the 40s, health and safety less of a thing. So when we started to study this more and more in the 50s and the 60s, we already had the material because we'd already built the reactors, so we could already study this. Fusion reactors, we don't have that. We don't have any way of generating that many neutrons other than a fusion reactor. So we have to use substitutes. So what we typically do is we use heavy ions, which is basically other atoms, and they generate similar damage, but not exactly the same. More importantly, they only generate a tiny, tiny region of material that we can actually study. When I say tiny, I mean a couple of microns. So this is a few human cells across. This is 1/10 the width of a human hair that we have to study. And we don't even have that much, because what happens when we shoot in all these extra ions is they then go and sit in a region. So we've fired in these ions. So we use the same type of ion because we don't want to change the chemically change our material. So we'll fire iron into iron. They then go and sit here. And now we've changed the structure of our crystal. That doesn't happen with neutrons. And we now have a massive surface here that will also attract our defects, that will change how that happens. So we have even less of a region of material. And as we up the temperature, those regions collide. And so this is what this graph shows basically. This is the region of safe material that we have to look at. And as we up the temperature, oh look, we've run out of material to look at that's actually representative of what's actually happening. And fusion reactors tend to get quite hot. So we're looking at new materials as part of this. So there's a lot of use of existing materials because we know them so well and we can study them. We're also looking at newer materials. So one material that we are looking at for one component is pure tungsten. And the reason we look at pure tungsten, so basically this is a map of the melting temperatures of some of the most common metals. Tungsten, filament in your old light bulbs, has the highest melting temperature of any metal, basically. And it is basically the only metal that essentially has a high enough melting point and has high enough conductivity to take the so in this case it's used as a heat sink, so we want it to take the heat away. So it's the only thing that has the conductivity and won't melt, basically. Apart from the fact that we're then introducing all this damage into it, which then changes the thermal conductivity of it. Not only that, we have even more transmutation. So we don't just have helium getting generated in it, we have literal lead into gold going on. And over time, the tungsten will actually transmute into rhenium and osmium. And this is literal lead into gold because osmium is not too far off the cost of gold. And so it's not even that the atoms are in different places. We've got different atoms in there. So that was basically a flavor of some of the challenges that we face. How am I for time? What are we on for time wise? Because I can do, I'll do a couple more then. Essentially, to give you a flavor of some of the new materials that we're looking at, and some of the newer than others. One concept is multi-component alloys. So instead of having your steel, which is 95% iron, your zirconium rods, which are 95+% zirconium, we make a stew. We take a bit of this, bit of that, bit of everything, mix it all together, and we form a crystal structure that is now wibbly wobbly because we've now put all atoms that are different sizes into it. And the idea behind this is that because you've got different sized atoms, it makes it harder for these atoms to move past each other. It makes it harder for migration to occur to form these defects in the first place, makes it more radiation tolerant. This is a very new field. A lot has to be proved in that, but that is one idea. Another idea is what we call oxide strengthened steel, where we put, if you can see these tiny little black dots, these are literal nanoparticles. This is so, and these are about 100 atoms across, and it's essentially these, we've put these tiny little particles in there. And the idea is that these particles will suck up the defects that we're putting in with the irradiation, and this will improve its tolerance for radiation as well. The problem with these is making them in the first place, because we essentially have to grind a nano powder. All sorts of health hazards associated with that. And then we can't melt normally when we're making metal. We'll just melt it, throw everything in, mix it up, solidify. Can't do that in this case because they won't. If you melt everything together, you'll just form a mess. You need these particles to be very small, so you have to grind them up and then grind your steel essentially, and then into it, which makes them very difficult to make. So these are some of the basically extremes that material science is going to try and get materials that can withstand the ridiculous intensity that is a fusion reactor. And that's me. Thank you very much. Yeah, go on. Yeah.
Sorry.
Yeah.
Regarding the tungsten melting point.
Yeah.
What temperature is that, and how does that relate to? Because the core of fusion reactor is very hot, so way hotter than any melting point. So how hot does it have to be to? I presume it's on the edges of the.
Yes. Yeah. So you've got different designs of fusion reactor. Oh, right. Sorry, the question was on the melting point of tungsten, the fact that a fusion reactor is, temperature of the sun. Yes. So absolutely, you've got it's the fusion reactor is millions of degrees. Tungsten melts at 3,400 bar the change. So different designs of reactor. But if you're talking about the confinement reactor, basically this is where I tap out and you get the plasma physicists in, who then basically get electromagnets to confine the plasma so that it sits inside the reactor and never touches the walls, so it doesn't melt all our materials. So there's a very basic, so you have a ridiculous temperature gradient where you're going from 1,000,000 degrees to a couple thousand degrees. But yes, if the plasma touched it, then yeah, there's instant vaporization. Yes. Yes, another problem. Yes.
On the first slide you showed,
Yeah.
you showed a lamp post,
Yeah.
and you said there was crystals that came from the steel that come out to the surface.
I didn't say that because it's galvanized steel, so those aren't actually steel crystals. If that's where you're going with that. I just said they were metal crystals. I was being.
Or metal crystals.
Yeah.
I still don't understand that, to be honest. The reason being,
Yeah.
I think I did tell you, I was a principal concrete engineer for AMEC for 28 years, and I've never seen that, nothing like that. And then in any my concrete stuff.
Yeah, because your concrete is not crystalline in the same regard. So yeah, it's made. The stones within the concrete will be their own subset of crystals, essentially. So concrete is completely different material in that regard. Essentially, if you take something, you melt it, you homogenize it more or less, and that solidifies. So long as it solidifies slowly enough, it will probably form crystals. And basically, the speed at which it cools will determine the size of your crystals. So that's why geologists have such beautiful crystals, because they're formed inside the earth and they're cooled ridiculously slowly, which makes your crystal size massive. And that's why you can see geological crystals. Metals, we tend to cool them much faster. You can't see the crystals most of the time by eye because they're tiny. Yeah. Yeah.
I'm really interested in how you talked about how when these fusion reactors first started, and that's when they analysed them, when they were actually building them. How must have caused a lot of problems? Do you know?
So I will give you one example of one of the problems that they discovered. So I'll go back to the welds. So they make your fission reactors out of ring welds now. So if you ever put a sausage in the oven for too long and it's cracked, right? Sausages are cylinders. This is the important part of it, right? If you put a sausage in the oven, it always cracks along the length. It always bursts open along the length. And that's because if you do the maths, basically the stress in the geometry of a cylinder will always mean it will crack up the length. That's why we use rings today, so that there's no weak welds going up the length. They didn't start by doing that. They started by doing plates, and they would make plates and then weld them together into the form of a cylinder. And now you've got this weak weld that's going exactly where a crack would want to go.
So it'd still be nowadays you have the rings, so
Yeah.
it's still playing in the sense that it's going round, but the dominant direction is around rather than.
Yeah, so basically it's like, so you're gonna have weak points, but you just don't want to put weak points inside weak points. So you don't want your weak welds inside the region that's got the most neutrons coming at it. If you don't want your weak weld along the direction that the crack's gonna go. So this is all about balancing, you know, what where you put things. They also used when they would do the welds, they would also use put copper wire along there, and so they melt some copper into the weld as well. And then discovered that that was a terrible idea, because if you put copper in steel, usually it's not too bad. If you put copper in steel and then you put it inside and then you irradiate it, that copper separates out really quickly and forms lots and lots of obstacles and makes your steel really, really brittle along the already weak weld. That's now also going up in the direction that you don't want it to go. Yeah, no, this is go, go for it.
Another really interesting picture I've seen before is the ship split in half.
Yeah.
And why was it that there's just this one big crack going right down the middle, as opposed to, well, lots of smaller cracks, you know?
So the other part of that was that they did the weld at 90 degrees, made it sharp, and so that's you've got this sharp angle, which then smaller area increases the stress, and once if you've got something that's brittle, once a crack goes, it only takes one crack to just go straight through it.
So why was surely that was along the whole ship though?
Yeah, but like it's going to fail once. I mean, if you look at crack in minute detail, then there'll be small branches coming off here and there, but you're not going to see that on the scale of the whole ship. Yeah, I mean, like once it's cracked, it only needs to, it's only going to crack once, and the stress is gone because it's cracked.
Yeah, and then that would just get bigger then.
Yeah. Once you've snapped something in half, unless you grab it and then you try and snap it again, it's not going to snap it up again on its own volition.
Is there no way to put some kind of sacrificial material between the neutron source?
They do. It's called water. So it turns out water is a fantastic neutron absorber, and that's why these pressure vessels can last 40+ years, because the water is absorbing a lot of the neutrons.
Fusion reactors, that's possible.
Not really. I mean, there's all sorts of weird and wonderful, quirky ideas up to and including the idea of liquid lithium walls, because we also, so for fusion, you need deuterium and tritium, these isotopes of hydrogen, which are more easy to fuse. It's very rare material, so in order to generate more of it, they talk about potentially having liquid lithium. So as that absorbs neutrons, some of that will transmute into your tritium that you want. So that is over the doors, yeah. But liquid metal walls, but yeah, this is basically where people are going, because out of the need to find something that works, or anything that works really. Yeah.
I don't know which metals put together to make it. You said before you that was a new idea to put various metals in like this. I don't know which metals to put in and what ratio you have.
This is a very young field. People are still working that out. So there's been a lot of there's been a lot of people trying various combinations and not having much luck, or having some luck in some aspect. So it's really good in this one specific thing, but then it's crap in this specific thing, and you need to have a good all-rounder essentially. So again, it is really young. There is none of that going into a nuclear reactor in the next decade or three, because it's such a young field. Yeah.
With the fusion issues,
Yeah.
how do you know the issues? Because as you say, the only way to test it is with the fusion reactors. I mean, as far as I know, I've never seen any that been the cause of the failed reaction or anything like that so far?
So the fusion reactors we have at the moment are most of the time switched off. So they switch them on for like 20 seconds, get a bit of fusion, and then switch them off again. And with so the models that they're looking at for fusion reactors are basically 5 years of operation, mostly switched off. And then because of that, you've got far fewer neutrons than 4 years of constant. Well, you still have more because it's fusion, but we know that amount of damage, so we can go up to that amount of damage because we know that. But then it's if you want a fusion reactor that's powering our homes, that's going to have to be on all the time for decades, and that is what we
Current
currently.
record for those 5 seconds.
Sorry.
5 seconds.
Yeah. So they're mostly switched off basically. So that's how we get fewer neutrons.
So this is a problem that would have to be solved before you have a feasible reactor.
Yeah, so that's what they're doing is they're going up incrementally. So do your fusion test reactor, operate it, plasma physicists do their stuff, get their work their stuff out, and then when you decommission it, the materials are there, and then the material scientists can take those and look at them and look at the damage, and then they can go, oh, okay, we can go a little bit more. So the next one will go a little bit more, and then we'll look at those materials, and then we'll go, oh, okay, right, what if we do this? And then so you have to go incrementally. Right. So what are we on? We've got a few more minutes, but yeah. Something else interesting. All right, okay. I will do you one more example of the desperation that material scientists are doing. Are going to. Come on. Can you go me back? Can you do me back a few slides, please, until we get to the table of elements? There we go. Right. So these things create unstable. These materials all absorb unstable isotopes. So another problem we have the neutrons create unstable isotopes, create a lot of radioactivity. So another problem we have is we want the isotopes that we do generate to have short half-lives. We want them to decay off, so that basically we're not producing nuclear waste for the next 1,000,000 years. We want the nuclear waste to decay off within the order of 100 years. So all sorts of quantum mechanics calculations as to why what elements produce absorbing this energy neutron, they're going to produce this isotope, it's going to be this radioactive. But fundamentally there is one material that is actually quite strong and will produce what we call low activation waste, so it won't be radioactive for the next 1,000,000 years, and ticks a lot of our boxes, and that material is molybdenum, or it is most of the isotopes of molybdenum. So some elements have multiple stable isotopes. Molybdenum has several, and most of them will decay to low activation waste in the time frame that we want, apart from one of them that will be radioactive for 1,000,000 years to come. So when you're enriching your uranium for your fission reactor, you put it in a centrifuge, and because you've got different isotopes of uranium, so you want the uranium-235, and that's your more fissile material, so you want more of that. And so you separate that out by basically spinning it in a giant turbine, and you can't separate these things out chemically because they are chemically identical. The only difference is a slight difference in mass. So you spin it in a centrifuge, and that basically separates your material by mass. And you have to use a lot, and you get you generate kilograms of uranium in this way, of enriched uranium in this way. We would need tons of molybdenum in this way. And people are starting to talk about basically isotopically purifying molybdenum, because that's basically one of the best ideas we've got so far.
Okay, he's a scientist and I'm not. What do you mean by isotopically purifying?
Basically, the bad isotope that's going to leave radioactive waste for 1,000,000 years, we want to get that out. We want to take that out and leave it that isotope purified from it.
Okay.
What percentage of molybdenum contains this isotope?
It's not that much, which is really frustrating, but it's just, I think it's, don't quote me on this, but I think it's on the order of about 5 to 10%. It's not loads, but it's still problematic. Doesn't have to be, sometimes it just doesn't have to be much, and it causes problems. Yeah.
Sorry, one more.
Yeah.
Applied system stuff out, consistently generate the blending you want. But does that mean you'd create nuclear waste of uranium to traditional kind?
No, so this is so you would purify it before you stick it in the reactor. So you just have a lump of molybdenum that's a slightly different weight, essentially. So that would never go into the fusion reactor. So you just, so that'd be totally fine. But also, the problem is that centrifuges are not a realistic way of doing this. Essentially, it's not feasible. So basically, we then have to come up with a new way of separating out isotopes in this instance, and that is basically another materials challenge, because we do it with centrifuges at the moment, but we do it for kilograms, not for tons. Centrifuges to produce tons of, in this case, hundreds of tons even, not feasible. So we have to come up with a whole new way of separating that molybdenum out. Another problem. Well, this is why everyone, you've got the old adage of fusion is it's only so many decades, years away. Because every time you think you get a bit closer, you find a new problem. And so this is why I hate putting like a time frame on when fusion will be here by, because so many people have done it before and got it wrong. What it's more about is just getting a bit closer. So it doesn't matter if it's 100, 200, 1,000 years, just so long as we do something that gets us a little bit closer.
I was just thinking, what if we make a plasma with them and use electromagnetic waves and so.
The molybdenum plasma would not fuse. It wouldn't generate the energy from the fusion.
No, just be separated. Because if you make a plasma from it, then you use an electromagnetic field because of the difference between the mass and the conductivity. You could separate it that way.
Quite possibly. I don't know how well that scales up. I don't, you then have to do the equation of you're generating tons of molybdenum plasma and how much energy you're gonna have to pump into it to do that, and how much energy you're gonna get out of the fusion reactor that you built with it.
Yeah, I was just thinking.
Yeah, no. There's that's not my area. But potentially, but I'd love to see how much energy that would take, I think. Right. Any more questions online, or are we happy? Sorry.
Thank you for coming, everyone. I hope you enjoyed that. The next sidebar will be on Monday, the 17th of April. So far, we haven't got a speaker, but I'm still working on it. So please do keep an eye out on our website. Our website has just been revamped. Simon at the back there has a brilliant paid job on it, and we now have a new mailing list. So I really would urge you to check out our website, because you'll find all the details, and there are subsequent sidebars for the rest of the